so that I know whether or not you can do audio and camera. To help the session interaction, I will encourage you to open your camera, even if you are not speaking. Most of the time, I will be speaking. So it is okay that you do not speak. But it will be good if you start your camera so that I can have a better sense about uh, whether or not you have a question or you want something, um, or have some additional information to provide you. If you are around a quiet place, you can also open your microphone. Okay. If your surrounding is kind of noisy, then you can turn off your microphone so that you don't interfere other people. Right? Okay, we are almost 40 people here. All right, we have 40 people. So I think I can close the poll. I know that the half of the people are able to do either camera or audio, and that's good, right? Right. Then let me start the agenda today. Share my screen. Right. Oh, that's my browser. Where is my PowerPoint? Okay, here we go. Oh, not this one. Good. Okay. So let's start the lecture today. I guess this is probably uh, probably the first time that you take a course that start at 7 a.m., right? And thank you very much for joining the session. So here, you have read the syllabus, so you know that the course in this course that we are going to write some program that is doing numerical calculation. So let me do a quick introduction about what is the numerical software and what is the numerical calculation that I'm talking about. So there is not a universal definition about the term numerical software. People use this term in a loose way. But my definition to numerical software is that it is the computer programs that is used to solve scientific or mathematical problems. Here, the scientific problems actually include engineering problems. Like, if you want to solve some problem happening in like making a bridge or build a house, that's supposed to be a numerical software. We do have other names like mathematical software, scientific software, technical software, so on and so forth. The key is that we use numerical methods and to solve problems. So the code would not look like very nice. Most of the time that the software that we are making are just code, and it provides an executable and you run it. put it there for like 3 days, and it quantum number and output several files, and that's it. That's the user take of a numerical software. And the second part is that it will include a lot of knowledge or information in the software, which we will have a little bit taste today. And you usually do not know how to write the code. Or let's put it another way. When you are putting together a software doing numerical methods, writing code is one of the easiest part in the work. Okay. Most of your time is spent on understanding what is the problem and understand what is the method to solve the problem, if there already exists a method, or you have to invent the method to solve the problem. Then you write the code to solve the problem. So until you have the ability to write the code, you actually have solved most of the problem. Okay, that's what we call knowledge intensive. And it also takes a lot of computation or a lot of computers. So we take advantage of parallelism, like or distributed computing, or using GPU or FPGA, or the so-called TPU or whatever processing units that people are coming up with. They are designed to detect a certain cluster of special problems, and that's what we do. And we usually have a scripting layer, and that is why that in the syllabus we emphasize Python and the C++, because the problems are complicated. So it doesn't make sense for you to write everything using C or Fortran or C++. We have a higher level layer to control command of the software. Okay. And this is one of my favorite quotes, and it explains the business we do very vividly. This is not a direct translation between Mandarin and English, but when I am describing what I'm doing or describing what is the necessity of my business internally and externally, in English we say speed is a king. We just want to run fast. If I'm fast, I'm good. Okay, of course we need to be correct. Okay. If I calculate a very wrong answer in the fast way, it doesn't really matter. It doesn't count. We don't do that. So in Mandarin, that is a quote from who? That's Jackie Lee? No, that's Li Xiaolong. What is the English name? I couldn't remember. Anyway, that's his quote. Let's say only fast is the king. Okay. So that's my business. So this is an explanation about what I do here. Oh, this is probably too small, right? I probably should make it larger. Let's see. Oh, that's good. Okay. This is better, right? I'm right now working in a company called Synopsys as OPC engineer or a software engineer for OPC software. We make software that tweak the semiconductor manufacturing photomask. So in a very quick way, that when we are manufacturing semiconductors, we place a light source somewhere. Then we turn it on and make the electromagnetic waves, which are light, passing through a photomask, which we have some patterns assigned or carved on those photomasks. And those figures or patterns are passing through the photomask and going shed on the silicon substrate, or what we call the wafer. We have photoresist, some chemicals spread on top of those silicon substrate, and those photoresists will react with light. That's why they are called photoresist. But you know that we are using the light wave we are using have a rather larger wavelength. Most of the time, it is like 193 nanometer. But the figures that we are trying to manufacture on the silicon substrate or photoresist is way smaller than that. So we need to compensate the effect. That's what we do when we are running the code we write on the photomask. So, well, not exactly on the mask, but what we correct the mask, so that we make it in a shape that hopefully on the silicon we will see a figure that is similar to what we have designed. Okay, and it takes a lot of calculation, and it is okay if you do not understand exactly what we are doing. We usually use like a year or two to prepare a new hire, or to ramp up a new hire after we have him on board. So it is pretty knowledge intensive, and there are a lot of information that is not written on paper because it is a niche market. So if we invented something, we just keep it ourselves without telling any people. Not even write a patent. So if you want to do things like this, you have to come to me or us. Then we'll tell you. Of course, we pay you if we hire you. And so this is a job description that I think we used a while ago for a role opening in our team. Okay. So you usually do not understand what is stated in the job description. But it is okay. For most of the job description that we have in the field, no matter it's OPC or aerospace or bioinformatics, they all look very cryptic and carries a lot of information that do not look like computer science, because they are not. For example, before working in the semiconductor industry, I was fluid dynamist. I solve problems in fluid dynamics, and my specialties are solving the conservation laws of what we call hyperbolic PDEs. The same set of equations here, here a big one, can be used to describe propagating waves in solids or compressible flows, which means supersonic or hypersonic flows. Fluids become compressible when it is approaching and passing the speed of sound. The speed of sound is the wave speed for the waves propagating in the media. So if you're in the water, your speed of sound is faster than the speed of sound in air, right? And while living on the earth, that when we are talking about speed of sound, we usually care about how we can fly, how fast we can fly, right? So that is air. So problem like this is about how to make things to control the nonlinear behaviors that happens in the air. Okay. Oh, this is some very cool problem. And there, of course, are many other problems like right now, the machine learning is pretty hot, right? Everybody is talking about machine learning. And that is also kind of computational problem or numerical problem, right? Usually you are using real numbers to do the calculation. And there are computer-aided design, engineering, and actually manufacturing. And there are computer graphics and visualization. There are many other types, but those are the examples that you probably have already heard of. Okay. Here, I have some question to you. Let me open the poll again. You elected this course, and I am wondering that what do you expect to see in your career later on? Of course, it does not need to have it doesn't need to have anything to do with the course. But the knowing that what you intend to have for. Later, I'll introduce how we prepare to have you to do some term projects. I can provide you better recommendation about what you should do or what you may do. Right. That's you like 30 minutes, 30 seconds to finish the poll. Allow me to have an idea about what you want. Right. So I'm not sure whether or not you like the online lecturing. It has good and bad. I think one of the good parts is that we have those online facilities that we can have in polls and doing some kind of offline interaction, right? Like if we have like 48 people in a classroom, we probably will get a little bit too shy to answer questions. Okay, so everybody have voted. So most of us, we have 36 votes for industry problems, and we have 9 votes for research. That's very good. Let's close it down. Later, I will use the result and try to ask you more questions about what you want to do. Okay, so this is the overview of our schedule. Okay. I have the course to be separated into 4 parts. Each part has 3 lectures. And in total, we have 12 lectures. But there are not a very clear boundary between each of the parts. It is just for you to have a general sense about what we do. So, sorry, this is right 2 parts, but actually there are 4 parts. You can say that the first 2 parts are for the architecture of computers. They are more about to review what we know or what we should know about computers. So we will cover about some fundamental software engineering and Python, or to be more precise, actually we will talk more about NumPy here. And then C++ and the real computer. Then we'll go through some basic about how to write fast code. First is array and the matrices. Then catch and FMD. So a little bit of the review to the computer architecture. Then after the midterm, we'll go into the 3rd and the 4th part, which are about how we organize our code, or what we should, what non-numerical problems that we need to solve in our software system, including memory, resources, and some techniques that you only see in modern C++ and some newer programming languages. Then we will talk about how to organize the code that we can make the system to work like a numerical system. Okay, so let me go on to the next page. Right. So this is the 4 parts I was talking about. And I want to remind us that we will have 6 homework assignments. and we will have a midterm. But because of the pandemic, I'm still considering what we do for the midterm. So this is a little bit uncertain. Okay? But if we do a midterm, it should be an on-site midterm. So you have to do hand calculation and some handwriting. You won't need to write a lot of code. Sorry, you don't need to write any code. You need to write down something. But I'm not asking you to use pencil or pen to write code on paper. It doesn't make sense. Okay? But instead, in homework assignments, you will need to write some code on computer. Okay? And we've had the final project. And in the final project, you also need to write code, but you need to come up with a good presentation of your projects too. So to help you to make the code as well as the presentation, I will ask you to turn in a proposal for the project. And you will be able to turn in the proposal in 3 weeks, in 2 weeks, 2 weeks from now. And you will have a duration of 5 weeks to finish your proposal. And during that period of time, before midterm, you need to discuss with me or among yourself for what you want to do for the project. We'll come back this later on. Okay, so this is the 4 parts or the 4 sections of our lecture. Let's go into each of the part one by one. First part is the fundamental. And today is the first lecture. If we won't have so many holidays on Monday, actually, the fundamentals will be in the second lecture. But anyway, I want to cover about what we do in software engineering. So here, engineering has 2 different meanings, right? One is the real engineering, one is software engineering. Software engineering is also real, but probably it's not so real compared to the real engineering. Anyway, I will have more explanation about the differences later on, but it is about automation and how we organize the automated things, as well as control the non-automated or the manual things. Then the second lecture is to introduce a little bit of Python. If you do not know Python, you are in big problem. Okay, so in order to be successful in this course, you need to know Python. And I'm not going to tell you how to learn it. And I'm not going to teach you Python. All right, you have to learn it yourself. My expectation to computer scientists is that you do not need to learn a programming language. Or, sorry, put it another way. You should learn programming language by yourself. You must not need a teacher for programming language. Okay. You probably need a teacher for programming language as a subject, right? It is a subject that you can study. You probably can come up with your own programming language. And that's what you can learn in the subject of programming language. But when you are learning a programming language, you should learn it by yourself. And then, so the purpose of the second lecture is that I want to tell you what are the important things in Python for numerical software and the programming. The same for the third lecture. I'm talking about C++. I actually will cover something very fundamental, very basic, like how to compile, what are the other types, OOP, and standard template library, polymorphism, because they are important for numerical software. But still, that is not what I'm teaching you. I'm teaching you the essence. I'm not teaching you the programming language. And the fourth lecture is to tell you how to control matrices or arrays and the basic operations that we will do with matrices. The real numerical software will do much more than that. but the matrices are still the fundamental that everybody should understand and be familiar with. Then we'll talk about cache, the memory hierarchy, locality, data layout, and a little bit of the tiling blocking techniques that we usually use for cache optimization. Then the vector processing. I think in this lecture, actually, we will talk a lot about your projects instead of the real SIMD. So using the lecture, we will introduce vector processing, but I will also actually starting from the 5th lecture, we will use the lecture hours to have more interaction about what you want to do in your project. Okay, projects are essentially important for our course and for your success. Then the 7th lecture is to manage memory. We will introduce 3 layers of the abstraction from the C level, or you can say the OS level, and the C++ level, and the template level. Then we talk about resource management using ownership and smart pointers. Yeah, and modern C++. Okay. Since starting from here, I think things are pretty detailed. So we can have better introduction later on when we are there. Same for the design techniques. Okay. Correct. So to study the course that we do not really have a textbook. There is not a good textbook for scientific programming. The reason is that most of the time, the textbook or courses for scientific computing is designed for people who do not know how to program. Okay. The course for scientific computing or scientific programming are not designed for computer scientists. As this is a course for computer scientists, right? So our problem is that we need to study by collecting the related information about the real scientific problems and the computer science subjects, like the computer architecture, like parallel programming or vector processing, and study by ourselves. But I do organize a lecture note that you can click here. Okay, so all the materials that I'm covering will be in the lecture note that I put online. So, for example, this is the first lecture about software engineering. So everything I cover in slides today, you can find it in the website. Okay, so this is probably the best resource for your study. And we do have references. The CSAPP is a very good textbook for computer architecture. And of course, there are some other documents for Python and C++. You can also consult the C++ standard specification, but that is pretty dry. And I will also encourage you to read the source code of Python, NumPy, and the Python tool that we are going to use in this course. They are well written, so they can provide you a very good reference about what can be done. Okay. Okay. Let's see. I think I probably need to move faster. Hold on a second. Where is my agenda? Okay. Here we go. So this is related to how we are going to develop our term project, but really it is a general observation and a guideline about how to develop numerical software. So we usually call ourselves as computational scientists rather than computer scientists because we are not. We call ourselves computational scientists. So the major difference between the computer scientist and the computational scientist is that computer scientists solve problems in computers. So if your computer has a problem, it's an OS problem or hardware problem, if you are a computer scientist or computer engineer, you should be able to fix it. But I am a computational scientist. When a computer, no matter it's software or hardware, has problem, I will go find a computer engineer or computer scientist to solve it. I won't solve it. As a computational scientist, I use computers to solve my problems. Okay, I don't solve problems with computers. Sorry, I don't solve problems in computers. I solve problems with computers. Computers are my tool to solve problems. So my problem is not the computer problem. My problems are the scientific or engineering or mathematical problems. Okay, so we oftentimes trying to solve some impractical problems that is not solvable without computers, like to carry out calculation of pi to 1,000,000 digits. That is not something human beings should try using our flash, right? We hand it to an automated machine, which is called computers. Another category is that we use computers to solve problems that cannot be solved without computers. Okay, if there are some problems that is too difficult, that on the contrary of computing pi, which is not really sellable, right? You won't pay money for somebody to calculate pi to 1,000,000 digits, no, right? But if I am TSMC, I may pay handsomely to a company that I am working for to solve the photomask problems that they want to solve, right? Because they are using the photomask to make wafers and sell the wafers to their customers, right? And then everybody has iPhone and can do Facebook Direct, right? So that's a happy ending. But that problem cannot be solved without using a lot of computers, right? If you have only a polygon, or let's say 10 polygons, and you want to carry out the adjustment of those 10 polygons, actually you can do that by hand. But say if you have 10 million polygons, then even if you have an army, you cannot solve the problem, right? You have to use computers. So that's the two categories of problems that we will develop software to solve for. And the order or the sequence of solving the problem is that first we need to know what is the problem. We need to see the problems. And that's actually one of the most difficult parts. Most of the time, we do not know what problems we want to solve. And you need to be very keen to problems and to be very keen in observation to see what is the problem. Then you can go to step 2, to generalize a theory in a mathematical form. It might not be a pure mathematical form. Maybe you will use some English or even Mandarin to describe the problem. But it needs some mathematics in it. If it does not have any mathematics, then it's very difficult to set up a program to solve it. Then you gain a solution, preferably an analytical solution, or if you can make it closed form, it's better. But not all analytical solutions can be closed form. Okay, It can be implicit solution. It's okay as long as it's in the mathematical form. Then we can start to think about how to solve that. Then the problem goes more and more complex. Then you got stuck. So you go with numerical analysis. Then you write some code to realize your numerical methods. Then you figure out, wow, it's either so useful in your lab, or it may be very useful in the field, put it in the market and you sell it. Then you got rich. Sorry, I lied. You won't get rich. The problem with solving scientific problems is that, yeah, you probably can get as rich as the guy who founded BNT. Yeah, they are very rich. Sorry, they actually are rich. But they are so rare. And you really don't want to have the scenario that you need to invent a vaccine for COVID-19 to get rich, right? That's unethical. So most of the scientific problems we want to solve are not so lucrative. So let's put it in this way. You can earn the handsome money, but that will give you a very good life and you will enjoy it. But you probably won't be turned into another Bill Gates or Mark Zuckerberg, right? Because there are so few people care about science on the earth. Okay, so that sounds incomplete. Oh, we have somebody. Oh, somebody have some noise. Let me try to have. Let me try to. Yeah, there's some echo. I wonder whether or not I can turn everybody mute. Yeah, I'm muting all. All right. Okay. So is there any echo anymore? Okay, that's good. Okay. So you can raise your hand. I think there's a button or something that you can raise your hand and ask some questions, and I can put you in under the spotlight, so you can speak. Okay. So we have a rather bigger class this year. So we'll probably need a little bit, especially online. We need some protocols so that everybody can have a good surrounding. And if you have any other question, any other problems, yeah, just put it in the chat window or anywhere. Send me an email. I will try to resolve it online. And don't be shy for asking questions. You can stop me anytime. So after we wrote a lot of code, we will realize that the problems, no matter it is a biomedical problem, it is a semiconductor problem, it is an aerospace problem, they all go to a common architecture using hybrid implementation. You will have a higher level things that is very easy to write, and you will have a lower level engine that is so difficult to understand but runs super fast. Okay, almost all the mature numerical software goes in this way. If you see some software is not going this approach, most likely it is not mature enough. Okay, so the software, although it does not have a lot of users, not as many as Facebook or Twitter, but the software will become a platform. That is because of this hybrid nature. So after you have a very high-speed, sophisticated computing engine, then anything above your engine will become the applications, right? Maybe the application is very limited, but there is actually flexibility in the higher level applications. So this is this is a hybrid architecture you can find everywhere. And that is what I want to teach us in the course. Yeah, that's a question, a very good one. Say, are we expected to build a model or system to solve the problem? Can you find any problems you want to solve in any area? Yeah, pretty much it. I think you get the point. I want you to find your own problems to solve. And but to fit in the setting of the course, the problem you want to solve usually needs to use real number, real or complex number. Okay, you cannot use integer, or let's say you cannot use natural numbers. Okay, because scientific problems usually are working with the real physical world, and the real world use real numbers, floating points, which we'll cover later on. All right. Yeah, you can follow up if you have further questions. Okay, so there are two basic camps that uses the hybrid architecture. First is the research code. Even industry have research code, which are some premature applications. We will have some problem defined and try to do very limited software engineering to try to make it a prototype. And in labs, like in universities or in your master or PhD program, you may come up with some research projects, and they will solve problems use writing some code, and they are research code. And there's also another camp that is a full-fledged application. This is most likely will happen in the industry, that we can sell those applications. Okay, there is a tiny, like 2.1 category, that is a scripting. They can be on top of a full-fledged platform, or they can be just some random scripts. Okay, so this things is the scripting things is even less mature than prototype, but can give you a very quick idea about what you want to do. Okay, and we'll be using C++. So we want to be fast and flexible in the same time. Okay, we are not making compromise. No, we want fast and flexibility. We do not trade speed for flexibility, nor trade flexibility for speed. Sorry, we want both. Okay, but we do sacrifice something. The things we sacrifice is the maintainability and the time to market. You need a lot of time to come up with implementation using this kind of uncompromisable speed and flexibility. Okay, so there actually are some guidelines about developing things like this, because when you are trade maintainability for things like this, you are trade a lot, and we need to do this very carefully, because unmaintainable code is the code that is very hard to sell. Okay, so even though we trade maintainability for those good features, we still do some management to the system. And we also want users to code without needing to know what is really happening in the architecture or in the software. So people, our user or your users, will be able to build up an illusion. Say illusion. I want to type it in the chat. Where's my cursor? Okay. We want to build an illusion for users that they can write programs. That's what we do. We create illusions for users. The reason that it is an illusion is that those users actually only know how to code on the platform we provide. They do not know general programming. They do not know general computer science, and they do not need to know. That is the value we provide them. All right, we are providing them value by limiting the scope they can write the code. But remember, we still provide extreme flexibility. Okay, the limitation is for their goodness. Later, when we are going into Python and C++, you will see more about what is the idea. Okay, so that's the qualification. We need both. So we take a hybrid implementation for the hybrid architecture. All right. Some more reason to Python. You can read it in online. So here are another questions. I want you to type some in the answer. So let me open the poll again. Okay, let's use like 1 or 2 minutes for your answer. Yeah, I'm seeing some answers coming in. And I think that we want to learn more about coding as well as making software. Oh, you can also like the answers that you are seeing. I guess everybody can see those responses. I would like to highlight Anwar answer. He mentioned about, he or she or mentioned about code review. I would like to introduce you code review. Actually, I will mention a little bit about it today. But code review is something unteachable. That it is impossible to teach. I'm going to like this problem. This answer. I cannot click one. We can have more discussions about why code review is unteachable in the following today or in the following lectures. I struggle a lot about this, and probably you can help us to find an approach to make some of the software engineering practices to be more introduced to us. All right, so let's do a browsing. Let me put an end, okay, so that we can move on. All right, so we do have, we want to develop something and put it on GitHub. Oh, that's good. And well, at least your homework will need to be on GitHub. Okay, I have released the first homework assignment. It's super simple. It's about writing shell scripts. Okay, and you can see a link in E3, and you have 1 week of time to finish it. Okay, and you will need to use GitHub to turn it in. So that will be one of the practice that I will provide you for software engineering. We will be using GitHub for most of the homework assignment. Well, all of the homework assignment and the term project proposal. But I want to give you an idea that GitHub is kind of a crippled tool. It is not a very good tool for software engineering. But it is an okay tool for some people who want to get introduced into software engineering. Okay. If you haven't touched other software engineering tools, it makes sense for you to think that GitHub is advanced. Okay, and I agree with you with that analysis. The reason that GitHub is not so advanced or not so good is because that if you want to have the full power of software engineering, you need your internal tools. Very good software engineering tools are always ad hoc to your own workflow. So every major companies have their own internal software engineering tools. We take advantage of open source or off-the-shelf tools, but we assemble them in a way that they become the internal tool that is tightly integrated in our everyday workflow. Okay, so plain or vanilla GitHub is not really so useful, but it will become very useful if you have a lot of your infrastructure built upon it. You need to write a lot of code to try it. Okay, and I see answers like advanced skills and thought in coding. Of course, we will cover that. Git flow, yeah, a little bit. Machine learning, oh yeah, that's good. Some acceleration, we can talk about that. Build a system is good, and design a project, that is one of the essence of the course. And software development, yeah, coding, and yeah, speed up. Yeah, the hybrid implementation is what we will do. Okay, how to write nice code. Yeah, good readability. Most of the time, the nice code is fast and may not be very readable. Yeah, that's contrary to the common belief that good code is good to read code. I would say good code is okay to read code, but it needs to accomplish some very important task. Otherwise, it will be useless code. Software design and modern C++, yeah. General software engineering, yeah, that's good. Right. All right, so that's pretty much it. So next part, I will talk about the term project we will be doing. I am a little bit over time. Do you need to take a break? Okay, let's take a break later. So I want to help you to know how to make a specification about a software project. When we are talking about specification, it's more or less like a waterfall kind of concept. Okay, you create a specification, then you write a code, then you deliver the software, then you collect the money, right? Or, well, finish your degree, whatever. It's a waterfall, top-down style flow of writing code. But that doesn't really happen in real world, right? You can artificially force people to believe that you can specify something, then develop it, then deliver it. Okay, but that is really an illusion in the making of software. What really happens is that you have an idea and you write it down, maybe in English, maybe in Mandarin, it doesn't really matter. Then you start to put together some code to prototype. Then you saw, oh, that probably work. So you develop the code, supplement the missing code in your prototype and strengthen it. Then you realize your specification wasn't so good. So you go back to change your spec or your description of the problem. So you see, it is really what they call the iterative process, that you keep iterating the design on and on. Then to some degree, then you can deliver, right? It goes into a circle, not a waterfall, okay? However, although the real development happens in the cyclic way, I still want you to write the specification. That is what I call proposal. Okay. I think I have the next page explaining that. Okay, the proposal. Even in a team that practices agile or Scrum development, we still write specifications. But the specification is more serving the purpose, or it solely serves the purpose of communication. Before you have something working, you need to tell people what you want to do. Like you are the students taking the course, and I'm going to grade your performance. So you need to tell me what you want to do. Like we have 53 people here in this room. Here, I'm not able to spend an hour listening you how you are gonna develop a software. You probably didn't have an idea at this point, right? So you need to sit down and think what you want to do. And if you don't write it down, what you tell me will not be exactly what you are thinking. Oh, sorry. Even if you write down, what you write down probably won't be what you are thinking, right? There's always a gap. But something written down as a proposal or a plan will be something that is always consistent, right? Your thought or the real plan in your mind may change. But what you read down and check in GitHub wouldn't change, right? So whenever you want to change your plan, your mind changes, you can go to the proposal and make adjustment, rewrite it, or just tweak the order or change some parts in it. All are okay. And I can track what you're thinking by tracking your proposal. So if everybody in this class, in this room right now, continue with this course, I will have 52 proposals and projects to grade. And I need a way to grade that, right? So the same thing happened. This is the reality constraints. And we engineers love constraints, okay? Never reject constraints, because constraints help you to design your architecture. Because I am teaching a course and you need to clarify your minds. So I come up with this structure to create a proposal, and you need to submit it, having this general structure so that I know how much you understand your problems, and I can give you in time and helpful feedback to your project. See, this is the way for engineering. We work together, or you and I work together to make your project successful. See, and in the real engineering team, it will be working like that too. Your manager or your team leader is responsible for your success. You make money together, or you try to work out the project together. If the project is successful, you both are successful, right? You probably are doing the hard working, but your team lead or manager probably is also doing the hard working to fight for more resources or bonuses or more time for you to work on the projects, right? He may need to collect a lot of the materials, information to convince the VP who is receiving like $1 million a year to decide what is the fate of your project, right? And your manager and you both want your project to be successful. So he works hard or she works hard on that. And you also work hard, and the interface of your communication are things like the proposal or the specification. And you can change it. Okay. And it is your job to make the communication process as organized as possible so that everybody understands what you are doing. Okay. So I'm going to grade your project based on those things. First, I want to see you do software engineering. Okay. Then you need to prove that you are correct. This is tricky. I'm not saying I can understand your problem. Say, like some of us want to work on some machine learning problems. I don't really know the machine learning. So I don't know how to verify the correctness of your machine learning project. But that's okay. I know what are the look and feel in a software system that you do the verification. You can say that's kind of a QA process. Okay, I want to see that you take that into account. But you might make mistakes. We all make mistakes in software development. Okay, as long as we catch those problems, that is okay. Okay, then the third thing is the architecture. I want to see that you have a well-defined architecture in your software. And the last part, over time, are missing from many students, and you need to be careful about that. You need to think about how you to present your project in the end. Okay? You need to consider that from the beginning. I want you to pick a project that can make you look good. See, I'm not saying you need to pick a project to demonstrate your excellence in programming. Or if you can do that, I'm all ears. I really like it. But the fundamental requirement of the project is that you look good in the presentation. If you pick a project, even though it may be hard or it may be ground shaking for the field, but you don't look good in the final presentation, then you won't have good grade in this part. Okay, so all those factors are important in your project. So I'm not saying you need to lie, and you must not lie. You cannot do A and present B and expect that I don't see it. That won't be possible. I can easily tell that you are not saying what you are doing. You need to say what you do. So you need to think about how you are going to present it in the end. Okay, and you need to be careful about this, but you don't need to worry about it, because as long as you start to think about it, you will be good in the final presentation. People have problems in presentation most of the time because they didn't think about it. That is the real problem. They pick a project from the start and started writing code, and the code looks very good, but you cannot put source code in presentation. Well, I can, because I'm going to teach you how to write code, right? But you cannot teach your peers or teach me how to code. You need to present how good you are. Then there will be a problem if you didn't think about it in the first time. All right, so these 4 factors. They are also covered in the, I think in the website. Let me put it out. Yeah, I think we have it somewhere like here, right? Oh yeah. Did I miss something? No, not yet. All right. So the website has all the information, so you can just come back and see what are the guidelines. All right. So you are free to ask any questions and to present the final project. Oh, that's a very good question about whether or not we can present in Chinese. No, you must present in English. Okay. Oh, but in the chat window or the Telegram, you can write Chinese if you want. I will write English. Okay, that's my commitment. I want to help you. I know that probably some of our students are not speaking Mandarin. So first of all, I may not speak Mandarin. Otherwise, not everybody can understand. But also, I want you to be familiar with all English working environment. That is how you are gonna succeed, I would say. Taiwan is tiny. It is kind of blessing, I think, because we are tiny, so that I think we are doing probably #1 in the world for combating COVID-19. But anyway, we are small. So if you want to do something big, you cannot stay on Taiwan. You can live on Taiwan and do something big. But your scope needs to be the whole world. And that's the whole Asia, I would say. And the English will be a very important tool for you because you do not expect anybody except China to speak Mandarin with you, right? And if you are going to work with China or in China, then English doesn't really matter. So we need to do most of the things in English, including the final project. But it is okay for you to use Mandarin in chat, in this buffer or in Telegram. But try to use English when you are writing email to me. This is your opportunity to practice, because I guess it could be kind of weird for you to try to find someone and say, hey, practice English to me, right? So, but you can just practice your English with me. That's my duty. All right. So all those information are online too. Will the slide be released? No. All the materials are already online. So you should read the notes instead of the slides. Okay, I'm not covering anything more except the pictures, the beautiful pictures, but those are not real materials. Okay. And I'm going to show you the project list. The project example list. So to help you, okay, you see that you really don't need a slide because all the guidelines and principles are already online in the notes. I make a list about what you probably can do. They are not a full format for the project description, but I provided some. Let's make it larger. Okay. I have some directions about what you can do. One example is how to make arrays. Looks simple, right? But this is very tricky in numerical programming. Columnar array again. What are the columnars? Some of us probably know, some of us don't, and it was reading. And graph partitioning. I did PDE calculation before, and this is a very important tool. This is one of the fundamental problems in EDA, electronic design automation, what I'm doing, Boolean operation polygons. It is classical, okay? And search, spatial search. This is almost a classical computer science problem, right? You do not build tree in binary form or in linear form. You build it in multi-dimensional. and how to build it in multi-dimension to do geometry search. And Voronoi diagram, again, and another geometry problem. Okay, those are all the directions that I am working on right now. Okay, so if you pick any topics toward this direction, I can provide you some information and discuss with you with more insights. But you are not limited in those directions. Okay, you come with different backgrounds. You know different things. So I love to see a variety of projects from you. I will be excited to see what you are coming up with. Okay, so you are encouraged to use your originality to try to do some projects. But those are the directions. Okay, you can try to match your ideas with those directions to see if they are of the same sense or not. Okay. Okay, so that's it. Do we have any questions? Okay, I think I can take one or two questions before moving on to the next part. Oh, how to stop share. Okay, that's good. Okay, if there is no other questions, let's move on.
Excuse me, Professor.
Yeah, go ahead.
I would like to ask, when we build a system or a model, will we expect to use both C++ and Python to build this system or model to solve the problem, or we can choose either one of the language to do that?
Which language or what languages are you preferring to use other than Python?
I prefer to use Python.
Right, and you prefer to use Python?
Yes,
Python
I'm not familiar with C++, and I'm more comfortable with using Python.
Okay, no, we cannot use Python alone because using Python alone will not give you the speed that we need. Python is too slow. I think I can't remember which, but there's a lecture. In the lecture, I will cover how slow Python is. So I assume that you probably didn't realize Python is very slow.
You mean during the process or in the efficiency? Oh.
Yeah. In general, for a reasonably complex algorithm, Python is 100 times slower than C++.
Yeah, yes.
100 times. And whatever thing like 10% or 50% slower than C++ is not acceptable. Not to say 100 times slower. So I want to let the class know how we can achieve fast runtime and high flexibility in the same time. If you use Python alone or any other high-level language alone, you won't be able to practice that.
Mm.
I want us to practice that in a software project. Okay, I hope that answers your question. But
yes,
if you have further ideas, we can talk. You write an email or send me some chat note or bring it again later today or in the future. Or we can make an appointment for some separate chat. Okay, all are okay. I love to have discussion with you, and those discussions probably will be important for you to be successful about your projects. Okay, yeah. So do bring your ideas. Don't be shy about got negative answers. You need negative answers so that we can have the ability to guide you to what the course wants. Okay. So another question I have here
Thank
is,
you.
yeah. Any other further questions? No. Okay. That answer the next one is well, the project, our personal project. If you mean that if you what you mean by personal project is that you personally own it, yeah, sure. I will require you to release your project under an open source license. Yeah, but that's the only condition. You need to release that as open source and using a valid open source license. But it can be anything. You actually can use other people's project. Like if you are, say, committer to like Eigen as a linear algebra library. Yeah, we can talk about how you are going to use that as your term project. Okay. So the next question is that is the class still be online next week? That's what I was told. Well, next week actually we won't have a class, right? Next week is a holiday. Do you want a class on holiday? Nobody answered. I guess not, right? So next week we won't have a meeting. But I was told by the department that we should go online for at least 2 weeks. So that will include next week. From my observation, we probably will stay online for a very long time. I hate that. I like to have face-to-face interaction with people. But tell you what, I have been staying at home for half a year, and my employer in 3 weeks ago told us that we can go back to office. But last week they told me again, probably you shouldn't go back to office. So I'm staying at home again every day. So I guess we probably need to get used to it. Yeah. But whenever there's an opportunity to go back to classroom, I would like to go back to classroom. So on the speed of Python with using the different interpreter solve the problem, that's what people thought, but they weren't very successful. Yeah, we can talk about that if you have some information about like PyPy, Piston, something like that. But they weren't very successful. And does the proposal also use English? Yeah, of course. You should use English for the proposal. And a good project presentation? That's a good idea. Probably should show you something. Let me try to work out something maybe after the midterm. Okay. But that's not a commitment. But I'll try my best. And will we learn how to use C++ to manipulate CUDA to do some numerical calculation? You can. Yeah, you will. But you teach yourself. I'm not going to teach specific tool. I will cover specific language like Python, NumPy, and C++, and Python 11, and some other libraries. But I won't cover them from end to end. That's your own responsibility. All right. So let me move on to the engineering practices. Okay. First, I want to start. Why do I have this page? Oh, I want to tell you something about engineering, but the typesetting is so bad. I don't know why I made it this way. This is what I'm going to cover in the engineering part. The keyword is automation. Remember, and recall that I mentioned that software engineering is different from real engineering. The conventional engineering, we are saying that we use scientific knowledge to make things that beneficial to people. Okay, so per this definition, of course, software engineering is engineering, right? Except computer science is very different from science. So it is computer science, but it doesn't use equations. It use very little equations. It doesn't have like vector analysis. It doesn't have, well, it does have a lot of abstract mathematics. But it, I came from an engineering background. Oh, I didn't have any degree in computer science. So I am a pure mechanical engineer. So I know a lot about fluid dynamics. I know a lot about electrodynamics. And I know engineering mathematics. I would say things in computer science look so different from the science that I have studied. My advisor actually categorized, my advisors, both of them thought they are scientists. They got degrees from mechanical engineering. They both are pure mechanical engineers like I am. But we work on mechanics. That's one of the most theoretical part in mechanical engineering. You can almost say it is it is a discipline that is extremely close to physics. But it was the physics like 100 years ago, when people still care about mechanics. And right now, people care other things in physics, so they call us engineers. But that's what we mechanics do. So we sometimes use the term scientist, physicist, and interchangeably to refer ourselves. Although we are mechanical engineers, we don't think ourselves as engineers. We are more like scientists. Because the real engineer who makes the building and makes the machines actually don't do what we do in mechanics. We solve equations. And you see that in computer science, those computer engineering looks even more remote. You are always dealing with specification, tests, coding conventions. Those things looks, one of my mentors put it in a very good way. It is management. That's his comment about software engineering or computer science. It's more like in management rather than engineering. But that is not entirely true. Software engineering is also taking advantage of mathematics and scientific knowledge. And the key is to use machines to automate the process. But the software engineering is in a more abstract form, because software itself is already automation, right? Software is already using machines to do work. And to engineer that thing, we are again use the same machine to automate what we have been automating. So it's kind of convoluted, right? That's why it is looking like management rather than solving equations or building a real machine, right? They are different. So the first thing to do is that we will do some basic automation, and we have some tools to organize automation, and we have some work left that cannot be automated, but we still need to manage them, right? So the note is here. You can go to the website and see it yourself. This is a poll, a very quick poll. Just yes or no. I really want to know the answer. Have you heard about that? Yeah. Let's do it quickly. It's just a yes and no. If you heard about it, it doesn't really matter if you know what it is, because I'm going to tell you. Just whether or not you heard about it. Okay. Right. We all got it. That's good. We have like almost a third. Sorry, less than a third. Well, roughly a third people knows about it. That's very good. And I don't know why they call it Sheben, and I don't really know how to pronounce it. That's a really weird word. But this is a Sheben. Okay, when you have a script and you can run it through shell, then the first line indicating which executable to be used to run the script is what Sheben does. Okay, that line is Sheben. Okay, so when you are running a script, you always need to write the first line like that, right? Now you know the name. Okay, it actually doesn't really matter what it costs. Okay, but it is very useful when you need to Google. You also can Google that the first line in the shell script, but that is convoluted, right? Having a term to coin that line is kind of convenient. Yeah, I want to introduce the most basic way to write about automation. That is to use your shell script. Okay. And to use a shell script, you need to tell which shell you want to drive your script. This is the Linux way to tell that I am going to write the bash script. But this is non-standard. This is more or less Linux specific. In a standard way, we do not have this BA. And it is no longer bash BASH. It becomes a shell script, not a bash script. And there's a difference. You can probably study yourself why there is a difference. That difference doesn't really matter when you are writing code in your own system or in an ad hoc way. But it will be important when you are communicating with other people. And there are some scenarios that people care about being standard. Okay, so don't take this Linux way as a scripture. Okay, this is not set in the stone. This is just for convenience. And the second portion is everything after the Sheben are optional. But I would say you always should have some documentation about what you want to do with this shell. Okay. Then comes to the setup. I prefer and I will recommend you to separate the setup of a program from its action. It's a little bit like in C or C++, you separate declaration from definition for the function declaration, right? For variables, there's a different rule. But then you have a clear sectioning, and people who read your script will have a better chance to understand what you are doing. And for each of the section, it is good for you to put up a little bit note in the comment form for what you want to do. Okay. And so this script does a very simple thing that you a clone of a GitHub repository. Okay. Oh, and there is another question that I didn't answer, which was that what do we expect in the midterm? Everything that we lecture before midterm. That's what we should expect. But I can tell you that I probably won't be able to test your understanding about vector programming because that will involve assembly. So I would say that is too much. I don't expect anybody to remember assembly language for high performance computing. Okay, if you really are in that business, you have to remember that anyway. You don't need to use your brain cell for that right now. Okay, so probably accept those specific SIMD or vector CPU instructions. I will test everything. Okay. Can the meter exam be answered in Chinese? You won't get any point in Chinese. Yeah, you can answer in Chinese, but no point. Is that fair? So you expect that everything in this course should be in English. Yeah. The only exception are the chat window. And if you occasionally find me in cafeteria, you can speak Mandarin to me. But during the course hours, including lecture and the midterm and the final term presentation, I will speak English to you, and you should speak English to your classmates. Okay, yeah. And you also notice that my pronunciation and even grammar are not so good. But I am very confident about my English because when I fight, I win. Okay, that's what I expect for my English. I don't expect my English to be as good as an anchor or be a reporter. No, I won't be able to do that. That will take tremendous efforts to practice a language. Just like my Mandarin is not as good as to be a reporter or an anchor, right? You probably don't have that good Mandarin. And it doesn't really matter. Language is for communication, just like how we write programming language. We write Python or C++ or Bash so that computers do what we want, right? So I speak Mandarin, I speak English, so you do what I want. Okay, so I encourage you to treat your practice of English in the same way. Okay, and the next question to midterm, do we need to bring computer to code? No. For midterm, all you need is pencil. You should not use a calculator. So no, you cannot bring in calculator either. And that is pretty old school, right? But in real world, when we are doing, okay, I had a meeting last week. That just happened as something very, very, very good. We were in a half day long meeting, running nonstop 4 hours, discussing something about our future development direction. And we were discussing something like floor planning, okay, to estimate what the how much overhead we may have for certain floor planning plan. Then we got some discussions. One of our colleagues stayed silent for like 2 or 3 minutes. Then he spoke up and say, I did some calculations, say that this floor planning will have like a 10% or 20% overhead. Okay, now that is an online meeting, so probably he used some calculator or something. I don't know, but with that limited time, you need to extract information from the meeting, and the fastest way for you to write down to carry out the calculation is actually using the OPAD. Just some white paper, some paper, and record the number, draw some diagrams. And if the number goes to a little bit too large, then you carry out the calculator and do the calculation and speak up. Okay, engineers do that all the time. Okay, so don't be afraid of paper and pencil. They are your good friends. Sorry, not girlfriends, good friends. Okay, so in the midterm, I want you to develop that kind of sense that you need to do calculation. You need to do some handwriting. Okay, and the tests actually are pretty easy. Most people will be able to finish that in 20 or 30 minutes. Okay, because this is a programming course. There is not much to test except programming. Okay, the midterm was designed in that way because that I want you to appreciate the fact that handwriting are a very good tool. I don't want you to think that is optional. Okay, take it as mandatory. All right. So this is hold on a second. I think I need a little bit. Where is my? I think I need some help. Oh, weird. I used to have my overview window, but it is gone. Okay. This is the slide I want to tell you that a little bit difference about shell variable and the environment variable. So in the shell script or in the shell, it doesn't really need to be in the script. In the shell that we can define a variable using the equality sign or assignment operator. There should not be any space between the equal sign. So you will assign the right-hand side value to the left-hand side variable. Okay, that is the shell variable. It is understood by the shell. And outside the shell, no, it's not there. But we can export the shell variable to the environment. So it will become environment variable. So the process you launch from the shell will be able to read and write. No, not write. Only read the environment variable. Okay, and there are many tricks in shell scripting to deal with variables. One trick. There are many tricks. This is just one trick. That you can give default value for return. Okay, say I unset this variable. Then if this variable is not set here in this line, and if I use colon and dash, everything following that will be the default value to the left-hand side. Okay, so when I echo this, there will be no such thing. But remember, this variable is still unset after this line. Okay, then I can set it. Then the same statement will print this variable because there are some values in it. Okay, there are other variants of this kind of trick, like if you replace a dash to equality sign, then no such thing will be set into this variable after the state. So if you don't run, well, you can test it yourself. Let me not to confuse you. And a shell script can set an environment variable and run that in a sub process to pass the information from the parent shell to the sub process. Like here, we export my environment variable. Then if okay, sorry, this is in the shell script, in this do something shell script. Okay, And in the outside, I unset my environment variable. So in the shell script, it does not receive the environment variable from the outer shell. So it will print my environment variable. Sorry, I got it upside down. This is to run in the subprocess. This do something is inside a subprocess, and it will set the environment variable in that subprocess. Because it is a subprocess, so it doesn't get outside of that subprocess. So when I am in the outer shell, I do not see my environment variable. You see this do something printed by the shell script, but the environmental variable in the outer shell is reset to nothing because the subprocess should not reflect back to the parent process. I probably should draw some diagram. I will improve that next time. And another way to run the script is to source the content in the current shell. So when we source this script, we are not running the do something script in the subprocess. We are running the content of that shell script one line by one line in my current process. So you can consider the second way of sourcing it is to copy these 3 lines or these 2 lines, copying them from the content of the shell script file to my current shell. So it is like running export my environment variable in the current shell. So of course, in the current shell, my environmental variable is set to what I want. Okay, this is the basic information to deal with environment variable and shell scripts. Bash have a very limited, or shell have a very limited control of scoping. If we are in Python and C++, the language scoping is much more complicated. You can do a lot of control. And sometimes it can also refer variables that is outside your own scope. But in shell, we have only one namespace, that is our own shell. You can create another namespace, but you will be creating another process. And process is controlled by operating system. Okay, sorry for messing around in the beginning, but this is to demonstrate the scoping of your environment variable. It's always controlled by the process. And in shell, we also use it for redirecting the input and output string. Both input and output are used, but here we only describe how we redirect output. And I would like to remind that many of you probably will find this material to be a little bit boring, because if you are familiar with Linux and Unix programming, this is really like Unix 101, but I still need to cover it. So the redirection uses the symbol right angle bracket. It will redirect the standard output from the process to a file descriptor or a file. So this does not need any explanation, I think. We can redirect both standard output and standard error by placing the symbol or mark saying, I want to redirect standard error number 2 into standard input. And this command will have its output. It's a standard output to be redirected to a file. Okay, so what I'm saying two things is that first we redirect standard output to a file, and then we direct standard error to standard output. Then, well, it doesn't make any change because we do not have any standard output, right? The location of this symbol matters. It will make a difference when you have some command that is really writing to standard error, like copy. If you put it in the wrong way, you still see that the copy have standard error printed on your terminal because standard error is not correctly redirected to standard output. And if you put it in the right way, you will see that the copy is redirected to a newer device. This is one common way for us to suppress output of a command. Okay. And you can only redirect only one output. So this is a use case of this grab command. You want to find some text and maybe send the output to a variable or to a file or to anywhere. You can use this dollar parenthesis to run the command and have the output to be assigned to a shell variable. But you will see something uncomfortable printed after you run it. That is the error message grab printed to your terminal. That is through standard error. So you do not want to see it, but you don't really want to see those error messages to go into your variable, right? Because in this case, we are grabbing something that should not be found in the current directory. And if you have this error message fed into my variable, then even though I am not finding anything, I will have content in the variable and my detection will be wrong. So I don't want the standard error to be combined into my standard output. So what I can do is that I only redirect the standard error to new device. So I'm sending my standard error to new device. You can say that in this way. Then I have what I want and I do not have the strange error. And of course, it has a problem. If I do not have grep, then this command probably won't give me any error at all. So my task might not be accurate. So in the setup region of your shell script, you probably will need to test, do I really have grep or not? If I do not have grep, then I need to have an error throughout to tell people should not run my shell script. Okay. And in shell script, we also do conditional branching. There are bash way and the shell way. I have to be honest that I never remember what they are, but you can read the manual online by yourself. What I want to tell you is you always need to write these conditional branches. Okay, this is an example for telling that whether I'm under Mac or I'm under Linux, I'm going to set a variable based on the value of number of CPUs that I can see from the system. And we also write functions. This is one thing that I think bash or shell is much better than C shell. Yeah, right now there are still many people using C shell, which is bad, right? Because C shell does not have function. Bash has function, so you can define a function and run it like a regular command. So here is a function that I kind of wrap some commands and redirect the results of it execution to some places I want. So you can notice that here I have a dollar symbol, and using the array argument is at column 2. It means that I want all the arguments starting from the second one. Okay. So the first argument I will be using that for the file name I want to redirect to. So I can run the command and have the output to be set to a file. And I'll also time the command I want to do. So I have timing here. So this is, oops. Okay, this is a running example. Okay, I would like to show you some project I'm working on right now. Okay, this is development environment that I am working with for my casual coding. Oh, we have 111 commits today, which is pretty nice. It is purely written in Bash. Okay. What it does is to set up an environment and building a lot of packages from scratch, from source. Let's take a look. Oops, now this is true. In build. Okay. Yeah, I'm writing some program, and there are some dependencies. Usually you will, if you develop on Linux, you can use the package manager to install the package. You are on Mac, there are some package manager on Mac. However, things will go south when you want to debug your dependency. Like, I write code based on Python, but what if there is something wrong in Python itself? Then I need the source code of Python, and when I need to build it from scratch, then I can go into the Python source code and to change where I think there's a problem, right? If I use the system provided Python binary, then I cannot change how it behaves. Then I will be doomed if there is a bug in Python. So this development environment is to build here, like this bash is to pull the Python from upstream, then build it from source. So when I am developing, I have both the Python source code and the binary that I built, and I can change any of them. So if you are working on software projects that has a broad dependency, most likely that you will end up with a development environment like this. You will be building all the dependencies by yourself so that you can debug your dependency. Okay. Okay, that is. Okay. So that's shell script. Any questions? All right. So next one will be Makefile. Why don't we take a 5-minute break so you can like I can go fetch some water, and you can think about what you want to ask, or do something that you should do. Okay, let's come back in 4 minutes at the 9 sharp. Okay. All right, we are back. So did I miss any questions before? If I did, feel free to bring it again. All right. Okay. So Makefile. This is the second tool I want to cover for automation. It is the import of Makefile or make is usually we're talking about the same thing. For make is a binary that consumes Makefile, and Makefile is the input file of make. It has a lot of versions, but the first version was created in the 70s in Bell Labs. The most popular one is the GNU Make, and that is a make that most of us are using. But Microsoft has its own make, and I think BSD has its own make too. Anyway, there's many versions, but they are all make. Okay. Make is a system that uses timestamp to keep track of the building process. Make was created to build software, so it is one of the earliest build system in the world. Before Make, people are writing shell scripts to run the compiler and build the code. Then there are some problems because sometimes people forget to run compilation. And at that age, compiling is a very time-consuming process. It is still time-consuming right now, but we have many technology to speed it up. At that time, people are saving CPU cycles for compiling. So Make came to a rescue that it will detect if a file is new enough for rebuilding, that it will have a file in the system, and that it will see if there is a target or the object that is to be built. So there's an association between the source and the destination. So if the source is older than the destination, that means the destination is already built from the latest source files. And if the source files or one of the source files is newer than the target, that means, oh, the target is out of date. So I should start the compilation or build process to turn the source files into the object files or destination files. That is Make. So this is the Makefile format. The whole section here is a rule. And keep in mind that for the second line, the first line is starting from the beginning of the line. But for the second line, you have an indentation, and that indentation uses tab. It should not use white spaces. If you use white spaces, I think that's a syntax error. The first line defines the target and the dependencies or prerequisites. That is, the prerequisites are the source. And each line This line under the first line is the recipe for the execution. And we can define variables in make. For example, that here I define the C++ compiler binary. This is the command, the rule to build the executable named hello. The source file of those two executable are two object files. And I'm using the compiler to take the object file and output to the executable. And of course, here the compiler is doing the linking job, not really the compilation. And I have two additional rules to really specify my source files. First is the hello.o object target, and it will depend on two source files. And here I'm really doing the compilation. And the same for hello man.o. Of course, this is a hello world program, so it doesn't really matter what we have inside because it only prints hello world. And let's do a fresh build. So we remove the files and we make. So it will run all the command or the recipes and build the thing. If we immediately run make again, make knows that everything is up to date. Nothing is out of date. And we can change one of the source files. Then you see that that object rule get executed. So we rebuild this hello.o target file. But hello.man target file is untouched. So we directly go to the linking of those two target files and into hello.o. And we can change the header file, which is part of the prerequisite of both object files, and we make. Then we see that all rules kicking in. So we got the full rebuild. So when we are writing make files, it is important for us to correctly specify all the prerequisites. This is also good and bad. The good part is that you can change the dependencies any way you want. The bad is that you have to always be right on your dependencies. And make provide some automatic variables. This $@ is the file name of the target of the rule. $control is the file name of all the prerequisites. $left angle bracket is the first prerequisite. Then we can use those automatic variable to rewrite our rules. Okay, here is to use all the prerequisites to link. Then compilation uses the first prerequisite. Okay. Make also support implicit rules, and we can also customize the implicit rules. The customization uses a percentage symbol for pattern matching, and we can use those patterns to write the rule that it is called pattern rule. Then accept our linking rule here. We still need to specify the target name and the prerequisite, but the compiling rules, there were two rules of the compilation, right? Is replaced by this pattern rule. We want to build any of the CPP file into the corresponding object file using this recipe. And the reaction is exactly the same as before. Okay. Rules make support of phony targets, which are fake targets. They are not really files, but are the symbols that we can make as target. So here we can define the default rule and make it request it as the hello. But there is not really a target named default. And make has a convention to use the first rule appearing in the make file as a default. So by placing this default phony rule on top, we can use it to redirect to the last rule, which is the real default. This technique is used oftentimes in make. Okay, that was make. Any questions? Okay. If you do not have time to type, you can always, I think you can raise your hand or do something. I think there's a button for you to click. Yeah, you can, like, I can click, I have a comment. Then I can give a microphone to you for you to ask something, right? So you can do you can do that anytime. Then I will get interrupted, and I can give you the microphone so that you can quickly ask what you want. Oh, we just mentioned about using English in lecture, right? There was another exception I forgot to mention. When you are asking questions in lecture, you can use both Mandarin, or either Mandarin or English. Okay, so it is okay for you to ask in Mandarin. I will repeat your question to the class using English. So it is okay if you don't want to use English for your question. Okay. All right. The next one is CMake. CMake is a complicated tool. It has make in the name, but it actually works very differently from make. In our sample projects, that there will be example for CMake. But also this is a tool that I think you should learn it yourself rather than I cover it from end to end. Here I want to tell you the essential parts for why we want to use CMake. The reason is actually to make it cross-platform. Okay. For example, we saw this
Oh my gosh. 到10点吗？
很多人在问问题。
哦，问题有。我这边有点无聊，他在从前面的统计开始教，
真的。
但他就只有 overview 而已吧，细节不会讲，就是整个浏览过去。
完了，完了，用选课系统，选课系统现在可以那个选课。
可以吗？不是11点吗？
对啊，11点。忘记了。
突然觉得他的图片错误也是有一点嗨。